morning, everybody. Thank you very much for joining Mastermelt's webinar. We're going to talk today about homogeneous catalyst and how to recycle precious metals out of it. So just a few housekeeping notes before Adam and myself are going to start. We have this webinar today. It's going to be lasting about 45 minutes, and we will have a Q&A session at the end that will be about 15 minutes. If you have to jump out at any time, or if you're not managing to attend, there will be a recording available of this webinar on the Specialty Chemicals website, but also on YouTube later on. All of you are muted by default and will not be able to ask questions orally. However, you do have a question section on the right side of the platform where you can directly address any wonders that you might have. You can write either to us presenters separately, or you can send it in the whole group chat. Yeah, and there is also the option for you to sign in via phone. You might have received the link on the email earlier today. So, what are we going to be talking about today? The agenda is as follows. We will at first uncover what is hidden value. So why is recycling precious metals important? And then where are the precious metals in your own productions? What are the materials that might be contaminated by precious metals, but that might contain them? And how do we extract that value out of it? And then in a second part, we will talk about all the challenges that homogeneous catalysts might have for the recovery part, because there are some challenges such as hazardous catalyst waste, or the fact that you might need a distillation or a scavenger solution, which might be a bit more complex. And so we will dive a little bit into the practical strategies that might be used to find the best route, and then find the innovative approaches that will get you the best recovery out of your waste. The third point today will be the waste management itself and how do you handle the metal. So we're going to be talking about how does the metal get back into your production loop, and how do you deal with transportations and all the regulations that are involved with waste management. Explaining a little bit how Mastermelt can be your one-stop shop when it comes to precious metal loop. And we will end today on a case study. This is a real life example of something that happened with a customer of Adam. And he will show you how keeping an open eye approach was really helping to find the solution and getting the best recovery out of that waste stream. Who is Mastermelt? Mastermelt is a company that started in 1985, so we will soon be celebrating our 40th anniversary. And we are now globally present. So it started in the UK, in London, and there are now 4 different sites in England. One site is in Germany, so in the EU. One site is a production site is in Singapore for the Asian market. And then we have for the American market also a site in Tennessee, USA. Our latest expansion is the site in Wilton in the north of England. This is our Mastermelt HomeCat Recycling Center of Excellence. And it is a site we're going to talk a bit more about later on, because it is the site that has all the focus on the scavenging and distillation capabilities for all these HomeCats that we're going to be talking about today. All these different locations and one common goal, it's a global focus on sustainability. We are now, again, we have been re-rated by EcoVadis this year as top 5% gold. And you will see later on a little bit the whole recycling processes and how this is at the heart of our thoughts all the time. Why precious metals? Why recycling it? Of course, this is a very high value commodity. We are aware of that. And in the recent years, elevated prices added a great pressure on industries that were using metals such as palladium or rhodium. And it's really in this little graph, you can understand how many industries that are vital to our economy require these platinum group metals. and then don't only just require it, they are reliant on a stable and sustainable supply of the PGMs. Um, the PGMs are now a critical raw material. They've been identified by the European Commission. And if you look at the carbon footprint of these raw materials, it's very interesting to look at the comparison between a primary metal, aka a metal coming from the mining industry directly, and a metal coming from the secondary part, which is coming from the industry, a metal that has already been used in a catalyst, for example, and that has been recycled. This going for recycling. This is a secondary source. And when you look at the secondary source, we do have 98% lower carbon footprint compared to the primary metal. And this is obviously clear. It's in different characteristics, and why it's that much lower, you can already think. When you have to go mining the metal, you go 2 kilometers deep into the earth, roundabout, and it's more than 100 degrees Celsius down there. So they do need to make it in a viable condition so that people can go and work and extract the metals. Only that part, compared to the recycling of a metal, has a huge impact on the carbon footprint. And then there's another couple figures that are interesting. The secondary supply of platinum, palladium, or rhodium really varies in the market, but we've seen that depending on the metal and depending on the year, of course, we're about at 20 to 30% of these metals that are being supplied in the market, which means that, of course, we still have a lot coming from the mines. But once you do have some precious metals in your catalyst or in your possession, then make sure to keep it in the loop and make sure not to just discard it because you don't know how to recycle it. There are always solutions to find, and keeping it inside of the economy is extremely important. We will now hit the more technical part and try to uncover a little bit where can this hidden value be found. So I will leave you with my colleague to describe a little bit our different material streams.
Thanks, Eleonora. So the first thing to note is precious metal catalysts can come in varying forms. Typically, this is a heterogeneous catalyst, a palladium on carbon, a platinum on carbon, or what we see more and more in the market now is the use of homogeneous catalysts. And this can contain a wide variety of PGMs, typically palladium, platinum, and ruthenium. So you'll be using these catalysts on site, but then these are maybe really the obvious areas where the precious metal is contained and when this product is used to capture it at the end of the process. But there are also some more hidden examples of where you might not be recovering the metal, and it's really important to capture all aspects of the PGM's residues throughout the plant. So you might find that you have some sludges, muds, and filter cake, or filter media, or filtration systems that are used, and it's really key to make sure these are cleaned out or the filters are sent for processing. Scavenger resin may be used for purification of the product in the early stream of the process, and also downstream, if we're looking at waste recovery, a scavenger might be used. So it's important to understand that these materials need to also be sent for processing because they do contain the precious metals. And one thing that's really is overlooked, and we're talking here again about homogeneous catalysts, is when there are some low ppm solutions. It might be a fine mix of different organic solvents that are left in IBCs, and there is some intrinsic value left in there. And these are really where we'll talk in more detail, where typically these are overlooked. Also, if there's PPE, rags, wipes, anything used in the process to where there's been some spillage, some cleanups, it's important that this is captured along the way and the operators have an area where they can dispose of these in a safe way, which is actually stored and kept ready for when you're sending off your spent catalyst. The catalyst can come in varying different forms, in a paste, in a sludge, or in a particulate. All of these are things that we can process. And also, what's a good thing to look at is what about the containers? When you receive your fresh catalyst in from a renowned catalyst supplier such as Johnson Matthey, these can all be sent to us as well for cleaning out and for recovery. And I mentioned here about the low concentrate ppm solutions, and often there are varying different solvents in this matrix. I put a list up here of some of the solvents we've seen: propanol, methanol, DCM. And this is not an extensive list, but we can handle solvents of high boiling point, low boiling point, and if they have a high and a low value. We're taking a really long-term approach to these solvents to look at, can these be reused, can they be repurposed, or can they be purified? To make sure we're trying to look at these from a sustainable viewpoint all along the way. So we've looked at the first part of our journey with Mastermelt. So you're looking at where are my precious metals? So we know where they are now. We know what type of materials I'm looking for and what can be processed. And typically what industries do these materials come from? Well, they come from pharmaceutical, agrochemicals, flavors and fragrance, and fine chemicals, all industries which use large quantities of these high value PGM catalysts. But now let's really key into what Mastermelts do and the journey we go on with a customer to get their metal value recycled. So really, the first 2 points here are really key to us to make sure we can understand the material. And before we've done this work, we can't commit, or we don't want to be processing material. We need to look at samples, analyze them extensively, and understand the full matrix and the composition of the material. And we know that some customers don't want to divulge a lot of information and want to do some of this work in-house, which we can help with. We can help facilitate this. We can provide samples and some processing methods. But really, to get to the best and the best recovery possible, we would stress that us doing the work in-house gives us the full screening methods available, and we're able to look at all the pillars of technology. And once we've done this full screening, we understand the material, we've identified what is the best process route, then we can move on to helping with things like transportation. If it's hazardous waste, does it need a TFS? Are there complications in how you categorize the material? We're here to help all the way along that journey. Then we move into the processing. We will have identified which is the most appropriate route, which makes it mostly economically viable and gets the most amount of metal out. After this processing, the material is normally and often will be sent for thermal pretreatment so that we can provide a fine ash powder, which is high in PGM concentration. And here's where we analyze the material and are able to return metal to the customer. Along the way there is some waste management involved. There might be some solvents that I've mentioned will need to be repurposed, and other byproducts along the way which we have recycled or disposed of.
Thank you, Adam, for walking us through this different process roadmap. That's right. There is a lot of sampling and research on the screening part in the very beginning. And we do have 2 sites in England that are specialized on this research and development. One of which being the Mastermelt Technical Centre, which is in Stevenage, not too far away from London. And the second one being this last expansion I was talking about in the very beginning in the introduction, our Mastermelt HomeCAD Centre of Excellence in Wilton in the north of England, which is specialized in this HomeCAD recovery, as I was saying earlier. These centers were created to accurately analyze the precious metals of materials and develop new recovery methods for customers' waste, which contained the PGM. And we use advanced instrumentation and have specialists in PGM chemistry and recovery. And the goal is to create really a tailored solution for each material, particularly for those that have challenging both because of their complexity of the chemistry, but also because of the environmental concerns. So in the pictures, what you see here on the top left is a part of the lab of Stevenage, and then the other pictures are the facility in Wilton for scavenging and distillation. How does it work when we get the samples, the screening? What is really the process? So as Adam was explaining, we do welcome our customers to send samples to the technical centers because they will undergo different types of trials to understand how to get better recovery. So for example, there will be the samples will undergo some thermal trial to assess the behavior when they are heated. We will get a full sample composition assay. And then the fire assay will also determine what is the PGM content. At the end of all of this, the lab will report some detailed findings that you will have available for all the samples that have been received. On the other side, the home samples that are being sent to Wilton, these will also go through different routes to understand what is the best recovery possible, and how do you make it efficient with the right selected method. So what they will do is trials with distillation, trials with scavengers. They will undergo some pre-treatments with some acids to release the PGM that might have been tightly bound to some functional groups. But we will also assay the temperature and see what kind of effects it has on your stream, as well as selectivity, for example, on scavengers. So it's all these different trials and errors to understand really how do I get the best recovery, but also is it economically viable to do it this way for me? And now we can deep dive a little bit more on the homogeneous catalyst itself and what are the challenges of the recovery. So what we saw is, on a little market background overview, is that the homogeneous catalyst market is growing. In 2020, it was about $4.4 billion US, and it's expected to reach $6.5 billion US in 2026. As Adam was explaining, these are catalysts that are being used mostly in the pharmaceutical, fine chemicals, flavor and fragrance, but also the agrochemical industry. And they do have some benefits. They have easier reactions to heat management. They're much easier to characterize and optimize the reaction because they're highly selective, and usually they have higher catalytic activity as well. But there are some challenges because very often, Adam was mentioning it earlier in the materials, there's some low ppm concentration solutions when we're talking about homogeneous catalysts, because it is very, very high volumes and very low concentrations of the catalyst inside. There's a lot of solvents, a lot of waters as well, sometimes to avoid flammability. And this is what we're trying to work on for the recovery. There's a couple points. We're trying to achieve high concentration of precious metal, low volume of residue with low flammability, low toxicity, and free of deleterious elements. And only with these characteristics will we achieve the best recovery rates. So maybe now Adam can explain a little bit what are the different processing streams that we can do for these complex wastes.
So the first question is how do we process a material? What technology do we use? Well, there's really three options here, three pillars that we all do in-house at Mastermelt. So the first one being the scavenger. We use some scavenger technology to absorb the PGM onto a solid scavenger medium, which we're then able to recover from. I'm going to talk in a bit more detail about each of these three in a second. The next one is advanced distillation or advanced thermal pre-treatment. There are some other areas which we can offer, like chemical treatment and smelting, but this is not usually appropriate for homogeneous waste. And on the next slide, I'm going to talk about why we might choose one of these different technologies. And it really comes down to the initial screening work and the composition of the material we obtain. So we really do fully understand the material and the matrix of the material and what's in there and the levels of each type of material. And we're talking here about doing some trials, but these can be low quantities, a few kilos, up to hundreds of kilos. And then on production, we can do anything between tens of kilos to hundreds of tons. So if we just work our way through some examples on this diagram here, first thing we might look at is what's the water content. If it's less than 5 weight percentage, then our next question we ask ourselves is, does it have any reactive solvents? And I mentioned earlier that there are a number of solvents we've encountered, and there isn't anything that we don't think we can process or haven't processed, and we'll be open to a discussion about any. If the answer to this question is, does it have a reactive solvent, is yes, then our technical team are pretty sure that the best route next will be to look at a scavenger trial. And here we'll introduce a number of different scavengers, various different processing parameters and look at which is the best, has the best recovery over time, and the quantity that is recovered in that time frame, to see where is the optimum level. We don't want to be over processing the material to chase those final few grams of palladium, where we have to look at it and analyze where's the right time to stop the processing. And if we go back and there's no solvents present, then the next question we ask ourselves is, what's the PGM concentration? If it's less than 500 ppm, the next thing we look at is, are there any co-catalysts, and what levels are these co-catalysts? If we say here it's a high ratio of co-catalyst, then the most appropriate technology to use next is an advanced distillation trial. It's worth noting that, okay, we say, okay, the best thing here is advanced distillation trial, but in parallel, we'll be doing that work with the thought process that is going to be the best, but we never write anything off. We want to also have a look at all the other options to make sure we're not missing anything and to make sure that the recovery is optimized. If we go back again and ask the question about the co-catalyst and it's a low ratio, then the next thing is what precious metals are present, and is there a mixture of these metals? If it's gold, palladium, platinum, then we would talk, next thing we would say is, let's do a scavenger trial. Again, not writing off any of the other options. If we shoot right back up to the top again, and we look at the water content and it's more than 5%, the first question we ask ourselves is, what's the precious metal concentration? And if it's more than 500%, and then that material doesn't contain any fluorine or iodine, then we would think the most appropriate route is advanced thermal pretreatment. So there's no additional processing in there. There may be some additions to the mix of the material, but we'll be looking to advanced thermally pre-treat it. Maybe there are some fluorine in there, and again, we can still treat this by thermal pre-treatment, but there'll need to be some additional halogen controls while we're doing that to make sure it's done safely and efficiently. If we ask that question again about the precious metal concentration and it's less than 500 ppm, the next question we ask is what metals are in there, and if there are only the one metal, then a scavenger trial would be most appropriate. And then we need to look at what metals are in there. If it happens to be iridium and ruthenium, then we typically see that a complex scavenger trial is needed. And what this really means is we would see that it's likely that more than one scavenger is needed, where we use one in the first phase, maybe for the first 4, 6, 8 hours, then we filter off that, and then we need to introduce another scavenger. Or it might be that we have to adjust the conditions of the solution. It may be that it needs to be agitated and stirred for a longer period, or it might be that we need to change the pH level, or we need to heat the material. So we spoke about the 3 different technologies, so let's have a bit more of an understanding of what these things actually mean. And what is a scavenger? Well, a scavenger is a functionalized material, typically a polymer or a silica, which is able to selectively bind the precious metals within the solution. Then we're able to filter that off. We can do this in a fixed bed, or we can do it in a stirred tank. So this means we can adopt this service on the customer site. We can help them with an engineering solution, install a fixed bed, fill that with the most appropriate scavenger after we've done the testing, and then we can arrange to collect the column, clean it out, refill it with scavenger, and send it back to them. And we can do this quite quickly. Often we see that customers are using this in a continuous process, so they have a couple of columns in process in a lead lag setup. They clear those out, put 2 more in, and the others will be sent for recovery, and this is in a constant loop. Also, what we see is sometimes the material is in an IBC or it's in a big tanker. The customer doesn't want to have to use any more technology, so we'll do this in the tank. And again, if the customer or yourselves, you don't want to be doing that on site and you want the material to all be taken off site, we can help with any of the needs to move the transport and any regulatory information that needs to be dealt with the Environment Agency. On the scavengers, I've got a little case study here where we worked on a very complicated waste stream. We mentioned before how these often are complicated and vary in different components, and this one actually contained around 5% weight of copper. It had varying levels of palladium and platinum. Yeah, and it had nitric acid. There was varying particulates, agglomerates, and precipitates in this mix, and what made it more complicated is the feed really varied. So from batch to batch, you might see higher levels of the palladium and lower of the platinum, or vice versa, slightly more copper, and there might be more particulate in one than the other. So we really had to look at this at the broad spectrum and then really have open eyes in how we're going to process from batch to batch. If we just revert back to the document I was showing you earlier and the diagram of how we make our decision, the water content here was greater than 5%. The metals weren't varied and less than 500 ppm. So naturally here, a scavenger trial was the ideal scenario. And actually it worked out really well. We screened a number of scavengers along the way, and the ones we came to in the end did a great job in recovering the platinum and the palladium. If we take a look at the diagram below, the material started off in a very dark green color, which indicates that the palladium and the platinum are containing in there. And over time, over about 14 hours, you can see the diagram gets brighter and brighter blue, which is an indication that the palladium and the platinum have been removed. We did this in a stirred tank to make it quite simple. The customer asked us to do this on site the first time, but in the long term, we will help them with doing this on their own site. The scavenger we selected was highly selective to the palladium and platinum, which you can see how it was selectively bound to the scavenger quite quickly. In the 60, 70, up to 90%. And then gradually over time, we got up into the high 90s, which is where we'll be looking to do every time. So the customers got a really high recovery. And also this scavenger in particular, the copper binds to the resin to start with. And then over time, the palladium and platinum displace it, which means we were able to also recover the copper for this customer. And what did the scavenger look like? So here's some before and after photographs of the scavenger resin once it's loaded with the PGM. And what's really interesting to point out here is the weight percent of the material. So from the starting material, what we're left with, the weight of the resin is only 1.3% of the bulk. So in the future, when the customer does this on their own site, what they're going to need to ship is going to be a low volume, high concentration PGM. And all the organics and any hazards have been removed, so it's easy to move this across board borders. That material is then sent to one of our sites in Europe or in the UK for thermal pretreatment, where we produce a fine ash. And I mentioned again, the copper is also available for recycling and the value of that recovered and returned to the customer. So what's next? The next phase we talk about here is the advanced distillation and what that really means. It's low boiling point solvents are removed from the matrix. They're boiled off and are held for further concentration or reprocessing. What we're left with is a product of a tar or a concentrate, which can then be sent for thermal pretreatment. Just to know that running a distillation process to recover PGMs does require some specialized design and conditions, and often we have to make additions along the way. So for every process, this is where we're optimizing what we're doing and making sure that it's the most effective. And I mentioned here about the solvents that are removed and what we do with those. So always looking at this in a sustainable way. We have some third parties globally where they're able to recycle solvents, or we look to move low grade, low value solvents, which can be used for fuel, or where there are some high value solvents, we look to have these fractionated and purified for further chemical use. So we'll always have that conversation about, are you able to use the repurposed purified solvents, and what are the specifications that it needs to meet? Maybe that it wouldn't meet what you need, but there are someone in the market that can use it. So we'll always look to move that on and recover any value there. And the last one we need to talk about is advanced thermal pretreatment. This is typically the way you would process a heterogeneous catalyst, by removing the water and oxidizing the carbon-containing compounds, which produces a fine, rich ash. We can do the same here we found with some homogeneous waste, not all. Often we need to make some additional additions to the material matrix to control the way it burns. The complexities to ensure that we control the oxidization. There are stringent rules for emissions and how this is controlled. So off gases must be treated by our gas abatement plant to make sure nothing is going into the environment that is hazardous. And as I mentioned before, Mastermelts, we can process materials containing fluorine and iodine. So advanced thermal pretreatment is really key to the whole refining and precious metal recovery loop, because whichever process route we go down, be it the scavenger or the advanced distillation, ultimately what we produce from those processes will feed back into advanced thermal pretreatment, where we create a very fine ash powder, which is even higher concentration of PGMs. And that's where we're able to assay and provide our customers with the metal calculations and the metal back.
Thank you, Adam. This was very clear with all the different streams. And there's something that you mentioned clearly, is that when there's all these solvents present, there's also something that is maybe more complicated, is that the material might be hazardous. And then in this case, to move material from one frontier to another, you do need a notification at the moment, right? And this is what is called the TFS, the Transfrontier Shipment Notification. And it is more complicated indeed to ship wastes. All types of transportation are a bit more complicated here. And this is something where we want to emphasize on the fact that we are here to support you as a customer of Mastermelt with this type of issue as well. So it doesn't matter what type of material it is. It could be precious metal coatings, some insoluble precious metals, some low concentrations, heterogeneous catalysts, but also homogeneous catalysts. Of course, not only low concentration, it could be anything containing precious metals, really. But more so homogeneous catalysts, because it's today's topic. In the case that you do have some hazardous material and it is more complicated, we do have a team that is dedicated to this regulatory issues and that has at the moment two options to help you and support you. One is that we provide all the documents that are required and give you support in this application. And the other option is that they can fully take over and handle the application on your behalf, putting all the input necessary without you having to get too much involved into this topic. However, we are also on an ongoing project here in Europe, working on some collection hubs in the countries where we're active, so that whenever you would have some hazardous material, we wouldn't have to wait several months until the notification can activate, and the shipment could be a bit faster. A last topic before we jump into the case study, and this is something that is very important to most of us, closing the loop. And how do you handle the precious metals? Once all the recycling part has been done, many of you are left with the question, all right, what happens with my metal? How do I get it back? How do I get my fresh catalyst back? And it's a couple options that are available to you. Either you do not need the precious metals back because you're not going to do a next campaign, and therefore you can sell the precious metals to us and we will credit you with the value of the precious metals directly into your company bank account. A second option is that the metals can be transferred to your catalyst supplier, so what is also called a paper transfer. We hold accounts called pool accounts for precious metals with most of the large PGM catalyst suppliers in the world. And this is an option that you can have as well. So just shipping virtually the metals to your supplier. But also if it's needed, the metal can be physically delivered to your precious metal catalyst supplier or to your location, wherever it is needed, really. To understand how the loop works, there's a little graph here. So let's say you start and you have your fresh catalyst, you start your campaign and obtain a spent catalyst that needs to be unloaded. You can get in touch with us and we will do the whole sampling screening part that we talked in the beginning of this webinar, and then help you ship the material to us at Mastermelt, any of our locations. We will then apply there all the tailored treatment solutions that we were talking about earlier and obtain these precious metals concentrates. These concentrates are then refined and we obtain precious metals, which are then sent to your fresh catalyst producers, such as, for example, Johnson Matthey, that will be able to produce your next batch of fresh catalyst. And there you go, the loop starts again. And this is how you want to keep the metal constantly running so that you have lower risks of price variations, and you only need to top up a little bit of your precious metals every time without needing to rebuy everything. In this whole loop, of course, some of you might wonder, how does it work with financing metals, with leases? These are all topics that you can contact us and we can discuss with you. We do have partners also for the leasing process of the metal, and we can support you on that aspect as well. So you do see here, it is really a one-stop shop solution where you do not need to think, okay, this was recycled. Now, how do I get my metals to my producer? How do I get all the supply running? This is something we will support fully and take care of. So you don't need to be involved in every single step of the way if you do not want to. Yeah. And now I would say we can close on Adam's case study. So you get a real life experience of what has happened with one of our customers.
So here we have an example of a real world customer who we needed to take the complete approach to recovering precious metal for them. It's a chemical manufacturer who had significant amounts of spent catalyst residues, which contained valuable amounts of rhodium. We identified really early on that the traditional methods of refining just weren't going to be the answer. They tried this in the past, we tried this in the past, and it had led to incomplete, uncompetitive returns, some environmentally hazardous processing, and the customer was losing a significant proportion of metal in both production and in the processing, making this really uneconomical to continue treating in this way. And in fact, they'd actually made a decision to stop treating and were unsure whether in the long term they would even go down this route. But we took on the challenge and we looked at how we were going to unveil this and really understand where the metal is and where it's being lost. So not only did we take on some samples and start to analyze it, we also looked at their plant and looked at what could be happening to the catalyst throughout its process. We looked at it right from the start, so when the catalyst was being purchased and where it was being brought into the plant and all the things that happened along the way until they filtered off the catalyst and into their waste area. Were there any areas in the process where material could be getting lost? Was it getting lost to the product and the analysis wasn't quite right there? And anything we could do along the way. So we mentioned before about homogeneous catalyst residues. The contents can be varied and the composition can be different. It's very different to the way you treat a heterogeneous catalyst, which is often uniform and repeated over and over again. In a homogeneous catalyst waste, there are varying different organic solvents which are blended together, and this results in a really complicated low ppm mixture. So to unveil this and to really get to the root of where the metal was, we conducted a meticulous research project. We identified that there were various components and the rhodium content of each one. And in this particular example, the material varied in its composition and also its physical properties from batch to batch, and even sometimes within a batch. So this made it very complicated and a real big challenge. But the detailed breakdown we were able to do by taking multiple samples from different areas of the plant as well as from within the waste allowed us to design a targeted recovery process and to optimize that along the way. So based on our analysis, we crafted a specific processing route for each of the different material types and the streams within those types, and also to have some understanding of where the variations might be and what we might need to do in processing along the way. This allowed us to optimize an efficient recovery of the rhodium and avoid any unnecessary processing for some of the simpler materials, because we did identify that some of the material didn't need extensive work. It didn't need multiple scavengers. It didn't need complex engineering solutions. We were able to thermally pre-treat it. We discussed earlier in the presentation that we would adopt bespoke processing and what these three technology areas are. So by leveraging our expertise in PGM recovery and doing this in a sustainable way, we were able to recover significant amounts of rhodium. And this not only provided the chemical manufacturer with valuable resales and the value of the metal back, but it also helped to minimize their environmental footprint by not having to, in the long term, ship vast quantities of material across borders. And to date, we've recovered in the region of $1.2 million worth of rhodium for this customer. And this actually happened mainly last year, where the price of rhodium dropped off significantly. So our success here really demonstrates our ability to optimize PGM recovery from really challenging waste streams. And we know that a one solution doesn't fit all. And this is why we made the decision to make sure we had all three technology pillars in-house. So we have full control and we're able to optimize these processes along the way and use, as we did in this example, all three technologies to get an optimized recovery for the customer. So offering this tailored and bespoke processing is key to getting a good return. And also the collaboration with the customer along the way and the open sharing of information made this really possible. Without this two-way dialogue and constant open discussion, it really wouldn't have been possible to get to the recoveries we're at. So just to conclude what we've been talking about here today, I want to just look again at the learning outcomes we discussed at the start and review what we've talked about and really what were the areas for you to look into. So the first one is why. Why do we recover precious metal? Well, we know that the PGMs are rare, they're of high value, and they're critical to many other industries. So it's key that we are keeping these critical materials in the loop and not always looking for virgin mined material. And what materials can we recover? Well, anything that has been in contact with or is the catalyst. So anything that can be contaminated with the PGM or is used in your process. And we're talking here mainly about liquids, but also it's key to look at the solids as well along the way and make sure everything is being sent for recovery. And how do we do the recovery? So we've looked at the three pillars of technology we approach and how we always want to adopt a hybrid approach and a mixture of all of these. And what are the strategies and what we look at to optimization? So the most important thing is a detailed characterization of the material to understand the composition, which then leads us on to offering a tailored approach and how we would use any of these three different technologies. And we've discussed the challenges. We know that it's challenging to look at recovery, and sometimes customers and companies overlook this. They understand that there's a low concentration, high volume of solvent, and maybe would look to have this sent for waste disposal because it's a lot of effort. But working with us, we're able to, as I said, characterize the material and come to a solution which is economically viable and in the long run worthwhile to not only the environment but to get some monetary value back. And we know that the materials are hazardous, so that's our team are here to help with moving the material across borders and making that as easy and as stress-free as possible. So I just want to thank you all today for joining. Eleanor and I's contact details are up here. If there's something you want to discuss in private, if you have any questions, or if you have a project you'd like us to start working on, please do get in contact. We're going to move on now to some question and answers. I've seen in the chat box a few things come up already, so we'll just have a quick look at those and start going through them. But please, if you have anything else, please drop it in the chat box now.